The last thing that we look at for looking at nuclear reactions is looking at the kinetics involved. And the great thing about this is it's the same thing we already have learned when we talked about kinetics of chemical reactions. And it's actually even simpler because all of our nuclear processes are first order reactions. So if you notice, we're going to use the exact same equations that we used when we talked about first order chemical reactions. We looked at the same integrated rate law, the same relationship to the same graph to get a straight line, and the same relationship with the half-life, and we see that the half-life for first order reaction is independent of the initial concentration. Remember that for zero and second order we see a dependence on that initial concentration, so this actually makes our life a little bit easier because we don't have to worry about that value. And so we can use these equations for decay processes in the same way that we used them for chemical reactions. So what we look at for half-life, and things got a little jumbled up here when I converted it over for the iPad, but half-life is the half time it takes for the radioactive isotope to decay to half of its original value. So it doesn't matter whether we start out talking about having, 20 grams or 100%, whatever it may be, each half-life, which in this case is 8 days, and after that time we're going to have half of the original amount left. So if we start with 10 milligrams of our iodine-131, after 8 days we have 10 milligrams, or if we start out with 20, we end up with 10 after 8 days, with 5, and then with 2.5, and we can continue on and on until we get smaller and smaller amounts, until we can no longer measure those amounts because they're too small. And this is the same thing that we looked at when we talked about the kinetics of chemical reactions in looking at the amount of product that we had left. So this table just gives you some examples of some different half-lives. They actually can go from microseconds to billions of years. For example, uranium-238 has a half-life of 4.5 billion years. You don't need to memorize any of these values or any of the isotopes. The reason I'm showing you this is to give you some perspective on these values and the different types of radiation that's emitted, and specifically looking at the half-lives. We see that for these elements up here at the top, some of them have very long half-lives, and the shortest one is actually 38 years, which means even for strontium, a sample of strontium, it takes 38 years for half of it to decay. When I look at those used for medical uses, we know that these have much shorter lifetimes in the hours and days region. Now, the things that have microseconds or seconds half-lives aren't going to be all that useful for medical purposes, because before we can actually get them where we need them, they're going to have decayed to very small amounts. And so these are more manageable half-lives, so that way they can be used for treatment, but not something that's going to stick around in the body for so long that we're continuing to emit that radiation long after the treatment should be ended. With the uranium-238, what we see is that's also used for dating objects. Carbon-14 is used to date objects, and we'll look at some examples of that in just a second. But carbon-14 does have its limits, and so when that becomes beyond that limit of carbon-14 data, then we can move to uranium-238 dating. You don't need to be able to predict the type of radiation other than what we looked at for the valley of stability for the beta emitters and the positron emitters, looking at that information. Other than that, you would have to be given information like for uranium-238 to know that it's going to be an alpha emitter. So carbon dating is a great way to figure out the approximate age of something. Now, I'm not going to be able to figure it out down to the last day, but I can get very reasonable values for the ages of objects. And the way this works is that in our bodies, because we are a living, breathing thing, we are taking in carbon, and in the atoms of carbon that are in our body, we see some proportion of them, which corresponds to the natural abundance of carbon-14. So as those carbon-14 molecules or isotopes decay now, they are replaced by more carbon-14 isotopes. However, when we die, or when any plant dies, such as a tree that we use to make a book, when that dies, there's no more intake of carbon-14. We're only losing carbon-14, so the amount starts to drop. And by looking at the ratio of carbon-12 to carbon-14, we can actually determine the age of objects, because we can determine when they were last living. Because typically, when trees are cut down, for example, it's used for some purpose, such as to make a book or build something. And while there may be a lag time of a few months or even a year between its dying and being used, it's not going to be hundreds or thousands of years. And so when we talk about the age of objects from carbon-14 data, we can say, yes, this object is 10,000 years old or 12,000 years old. We're not saying it's 422 and a half years old, but it does give us a very good idea of how long things have been around, so that we can start placing things in context with one another. So carbon-14 data, we look at the half-life, which is 5730 years, so 5,730 years. We're worried about this carbon-14, carbon-12 ratio. And it works great up till about 50,000 years. That's pretty much the upper limit for carbon-14 data. Beyond that, we have to look at uranium-238 to lead ratios to figure out the age of something. Now, one thing we know is that there are variations in the carbon-14 percentage, or that natural abundance, over time. And one way we figured this out is by looking at trees. When you look at rings of trees, that each of those represent a year. And if we look in those rings, we can see different proportions of carbon-14. Now, again, it's not changing things dramatically, but it can change things by a few thousand years, depending how old that object is. When we go beyond the carbon-14 data, then we can look at uranium to lead dating. And so for this is objects more than 50,000 years old. So when we look at the Earth, for example, we find that there are rocks that are more than 4 billion years old. They are meteorites. Whoops, that is spelled wrong there. Sorry about that. Meteorites that are 4.5 billion years old. And the universe is 13.7 billion years old. And when you think about our little speck of time that we are occupying in that spectrum, it's just so small. And if you've been watching any of the Cosmos series with Neil deGrasse Tyson, he kind of uses this analogy that compares the history of the universe to a calendar year. And when we do that, so if we imagine that this is the length of one calendar year, this is the history of the universe, and so all these things are going on, this is time passing, and everything up to this is everything else except us. And where we occupy this is about the last 60 seconds of that year are what we are actually occupying in history. So if this was our year, this is day 0 and this is day 365, we get the last 60 seconds. So that's how little bit of our history is actually in the entire history of the universe. So that finishes off the material we're covering in Chapter 19. I recorded this video so that we could have time on Thursday to just answer questions and go over anything you want to review before we have the final exam. If you have other questions, please feel free to post them on Piazza, either under the notes so that I can answer them in class tomorrow, bring questions to class tomorrow, or you can post questions on the regular Piazza discussion board and I will answer them there. I will have office hours on Monday and Tuesday from 10:30 to 12:30 to answer any questions as well. Remember, our final is on Tuesday from 8:30 to 10:30 p.m. A seating chart will appear on Blackboard but may not be there until Monday. The Chapter 18 homework is due on Thursday. Chapter 19 and the bonus point assignment are due on Friday, and that bonus point assignment is optional. It will not affect your final course grade regardless of what the average says on mastering. If you have any questions, please let me know. And if not, have good luck on all your finals and enjoy your summer.